One of the major challenges from modern neuroscience research is to understand the dynamics of motor learning and sequence acquisition beyond keyboard pressing tasks in the laboratory and in more naturalistic settings and actions. The goal of this experiment is therefore to understand how people learn a sequence of actions by stepping, similar to a dance. Inspired by the established Discrete Sequence Performance Task paradigm developed by Professor Willem Verwey, participants are given explicit sequences of fixed length to learn. This experiment describes the setup of how to collect data and how sequence learning processes can be elucidated from the results. Hi everyone, my name is Dr. Russell Chan and I'm a Marie Curie Research Fellow in the Faculty of Behavioral Management and Social Sciences in the University of Twente, the Netherlands. My research is in modern neuroscience and investigating ways to improve motor control performances. The current task is my modification of the classical Discrete Sequence Performance Task paradigm that was developed in the 1990s by Professor Willem Verwey. The DSP task, as it is affectionately called, is based on learners practicing short sequences of between 3 to 7 stimuli that is usually performed on a keyboard. The responses are spatially compatible with the stimuli, meaning that each finger is therefore mapped to one response location. A great deal of theory has been developed over the years that outline the cognitive mechanisms behind this task. However, we can do much more by making the DSP task more ecologically relevant and naturalistic, like what we do every day with our body and limbs during work and leisure activities. The key advantage of the current modification is that we can utilize and investigate the whole body and further unravel other complexities like the optimization of limb control across the upper and lower body parts during the learning of these sequences. This benefits the extension of theoretical understanding and individual differences between learners that allow us to understand why some learners choose certain strategies compared to others. Lastly, this dance step DSP task can also be developed into a formal program to train diverse populations like the elderly, aimed at increasing other peripheral parameters like balance control and falls prevention. Let me show you how the dance step DSP task can be set up in an experiment together with the utilization of advanced motion capture system called the X-Sense to increase the inference of results. The procedure and data outlined in the next sections was performed in accordance with human ethics guidelines approved by the University of Twente's Behavioral Management and Social Sciences Ethics Committee, filed as number 210390. You will need the following equipment before you begin: a modern personal computer or laptop, the ePrime software, either version 2 or 3, a display for the stimuli, a commercially available dance pad, and another software called Joy2Key that is free to download to map out input keys. If you're also interested in using motion capture with the X-Sense bodysuit, you will also need another modern personal computer, preferably with an i7 equivalent processor, the 3D motion capture software called X-Sense Analyze, and the suit system. And in this case, we are using the MTW Awinder, an Ethernet router network hub for sending and receiving event markers from ePrime, a weighing scale, and tape measure. In today's setup, we will be using the MTW with 7 sensors so that we can collect the data of lower body limb kinematics and the center of mass changes that is provided in the X-Sense Analyze software. I will be the experimenter today, and Elvis will be today's participant. Participants are firstly briefed about the purpose of the study, outline their rights to leave at any time during the experiment, after which they provide informed consent. Participants are then asked to remove their shoes to measure their feet size, height and weight that are required and entered into the MVN Analyze software for accurate modeling of the 3D figure and center of mass. Afterwards, a total of 7 X-Sense sensors are attached with Velcro binds from X-Sense to one of each foot, shin, thigh, and one on the pelvis. We next perform a calibration procedure for the X-Sense. The participant is instructed to stand straight, both arms hang by the side, which is known as the N pose, and wait for the researcher to start the procedure in the MVN Analyze software. The researcher then signals the participant to walk 4 meters in a straight line at a normal speed, turn around and walk back to the starting position. MVN Analyze then processes the calibration procedure and notifies when a good calibration result is achieved. Otherwise, it has to be repeated. The E' script is then executed. This one is a go and no-go version of the DSP task. Participants watch 6 different stimuli positions being presented as a sequence before a go or no-go signal, indicated as a blue or red plus sign in the center, tells the participants to proceed with responding. Each time the script is executed, we enter both the subject number and the session number, which indicates the training block. There are a total of 24 trials of 2 sequences with 6 stimuli positions, followed by a short 30-second break. Then another 24 trials are shown. There are a total of 6 training blocks, but this can be altered according to the design of your experiment, and also the number of stimuli can be altered. After each training block, there is a mandatory 3-minute break, and after 3 training blocks, a mandatory 10-minute break is given for much longer rest. At the beginning of every block, participants are reminded to quickly and as accurately as possible respond and then return back to the home position. We merged participant-level data to form a completed data frame for both the E' behavioral and XSense data. Here, we show some exemplar results and visualizations based on the data of individual participants and also factorial-level analyses on the learning blocks and individual foot-level performance. This figure shown here corresponds with figure 5a in the manuscript, whereby it shows the visualization of raw response time in milliseconds for the y-axis for 384 trials that were performed by each subject. You can visually see that across majority of the participants, learning of the sequences can be inferred from the decrease in response times from the repetition of trials, that is our time series data on the x-axis. Do take note of the different pattern of response times changes between participants at 18 and 28 that is highlighted in red boxes. This suggests that during the learning phase, different learning styles or strategies in dance step DSP task performance were adopted by the 2 participants. This next figure corresponds with figure 5b and shows individual participant latent learning curve response times across 8 learning blocks. On an overall, except for a few participants, most participants showcase a decrease of response times from block 1 to 3 and then less improvements from block 4 to 8. The current figure corresponds to figure 6 in the manuscript. The use of linear mixed effects models is an emerging method of understanding response times changes across blocks for the entire group whilst accounting for random intercepts, which in this case are the participants. This figure shows that the response times of each accurate-only dance step for sequence trials for all 24 participants. The y-axis are the response times in milliseconds, shown with the respective 95% confidence intervals, and the x-axis are the blocks. This figure highlights that most of the learning occurred from block 1 to 2, although latter blocks still show decreasing response times all the way to block 8. Interestingly, the average footstep response times for the sequence execution in the dance step are relatively short, considering that key press responses are between 200 to 400 milliseconds. This figure corresponds to figure 7 in the manuscript. The figure shows a linear mixed effects model of step-level response times across the blocks of accurate-only sequence trials in 24 participants. The y-axes are the response times in milliseconds with their respective 95% confidence intervals, and the x-axis are the different step positions, with each of the lines highlighting the different training blocks. The dance step DSP appears to showcase a different concatenation pattern, which means that a usual slowing of the 3rd or 4th position, indicating a chunk separation and limitation of working memory in key press DSP, is not evident in the dance step DSP task. Instead, the slowing occurs in the 6th position for the dance step DSP task. This next figure corresponds with figure 8a in the manuscript. The y-axis represents the center of mass velocity in meters per second, and in the x-axis, the first training block versus the 8th, which is the last training block. The colors represent the two different participants that are highlighted earlier, suggested of using different strategies to learn the sequences. The box plot figures shows the spread of the different velocities for each of the 48 trials in each block. Here you see that participant 28 shows development of more variability and a larger spread of the values for the velocity of the center of mass in the x vector direction compared to participant 18 from block 1 to block 8. The changes between block 1 and 8 for participant 28 with regards to sequence performance is what one would consider with accordance to Nikolai Bernstein's classical theories of the freeing of degrees of freedom in the center of mass with model learning expertise development. The purpose of this video is to accompany the manuscript that describes and outlines the methodology in much greater detail. You'll be able to access all the materials, scripts, and codes in the links to the open science repositories that are within the manuscript. You should also have a very good idea of the connections of the different equipments so that the experiment can be replicated wherever you may be. This dance step DSP task covers several shortcomings and provides new avenues of research compared to the usual keyboard DSP task. Firstly, we're able to investigate whether the difference of limb effectors compared to response locations arise from the same underpinnings as the usual DSP task. Here, the dance step DSP task has two limbs in which the learners must utilize the response to 4 different locations. This can give rise to different modal efficiencies that come from cognitive preparations and therefore strategy differences. It is fascinating to investigate these individual strategy differences. Secondly, we're also able to investigate interesting kinematical variances that change alongside response times performances with the X-Sense motion capture system. Limb dynamics and center of mass are important variables that can reveal whether different phases like the pre or during movement dynamics are predictive of sequence performances. And this can therefore reveal whether cognitive or modal processes play a more important role during the development of this expertise. Lastly, we're very excited about the future applications of the dance step DSP task in more formal training programs being applied in diverse populations like the elderly. The utilization of X-Sense allows for the experiment to be portable, and the experiments can therefore take place at rehabilitation centers to further assist and develop programs to help the elderly improve their overall physical health. There are so many different applications of this work, and we're very happy to share it with you and other researchers to utilize it for future studies. Thank you so much, and take care.